All right, so let's get started. So last time I had a video on the basically static balancing with forces, buoyancy force inside of liquid, something like that. And now we're supposed to study how the liquid is going to behave when it is in motion. So the liquid itself is in motion. Although you can still study when something is in moving liquid, it's just a little more difficult. So we're only studying liquid itself, how the liquid would actually move, and things such as how fast it moves and how much pressure it has inside, and the height of the fluid. So those things are our interests. So we'll start with ideal fluids, and you can think about ideal fluid as an idealized version of actual fluids. The realistic fluids have things that we cannot study at this level. They're just mathematically too complicated, and we already have gotten used to idealized situations such as a point mass. A point mass is just an idealized situation where the mass has very small extent, and that extent does not really affect our calculation as much, and we'll just consider a mass as a point mass, and a point mass does not rotate. So later we introduce solid objects, rigid bodies that can rotate. So the shapes do matter in the rotational inertia calculation, and also how much rotational inertia affects the angular acceleration and also kinetic energy due to rotation, right? So all these things are added in as details start to get revealed with more mathematics added into it. So in order to study fluids that are slightly non-ideal, then the mathematics that we need to add is a bit too much at this level. So we'll just make the fluid idealized. So what exactly is an ideal fluid? And there are different requirements. Basically, in order to be ideal, you have to basically let go of some of the details. So let's think about ideal fluid. So a fluid probably shouldn't have any internal friction. So if you have any internal friction, then if you think in energy conservation terms, the internal friction is going to cause some mechanical energy loss. So once you have mechanical energy loss, then you're likely going to, well, you're not able to use energy conservation, mechanical energy conservation anymore, right? So it's going to be difficult. So we need to get rid of friction. That means the fluid cannot have friction. So friction inside the fluid manifests itself as drag. So if you drag your finger along water, well, you feel minimum amount of drag, not much. You're used to it, so you're not really paying attention. But if you say you're driving on a highway, you just lower your window, you stick your hand outside, facing the air that's flowing against your hand. You can feel the drag is quite significant, especially you're driving on a highway. So that kind of drag needs to be taken out so that fluid can just kind of smoothly flow around without any loss of energy. So that is one thing we need to make sure. So it's first we want to take away so non-viscous flow, so no friction. And okay, what else can we idealize? So let's imagine a faucet. If you just turn on, water starts flowing, and sometimes it's kind of turbulent. It depends on how far you open up your faucet, and at certain point, the faucet could actually be very still. The water just flows down with very little noise, except for the water splashing against the water flashing, just kind of splashing against your whatever is underneath your say collecting water. Say you have a cup there, right? So the water that flows down with very little noise, and if you stare at the liquid, the water flowing, you can almost see no motion because this shape is maintained. Okay, so with that, and you can imagine this type of flow is steady. So the steady flow means the shape of the liquid doesn't change with time. Although maybe at the starting point, water flows less fast than further down because gravity pulls water down, right? Water should accelerate, and the cross section of the water stream is actually getting narrower and narrower until it probably breaks into droplets, and then it would actually be noisy enough, right? If it's never breaking into the droplets, if it's just a stream of water getting thinner and thinner as it comes down, and then you almost never really hear it, the sound, you almost never see the change of the stream. So this idea is an idea we can use for ideal fluids. So kind of static flow. So if you're say water, your water molecule, you're passing through a certain location, you'll be moving through that location with a predefined velocity vector, and the next water molecule comes through the same spot will actually go and do the same thing. So it's almost like there's coordination among the water molecules. So whenever they're going through the same spot, they have the same velocity, they have the same pressure. So the uh, the the shape of the liquid never change. So it's kind of a static, stationary flow in that sense. And we also don't want any rotational flows. So rotational flow will be a little curl, an eddy current, because the eddy current represents energy. So stationary, this is basically time independent, right? So the velocities are only dependent on the locations, right? So irrotational flow means you don't have any eddy current, any curls. There's no drain. There's no drain to kind of rotate around because that rotation represents some energy that we're not able to account for. So without that rotational energy, then everything else can be accounted for. So irrotational flow, there's uh, no eddy current. Okay, so basically kind of stationary, static, non-viscous, and irrotational. Let's see what else we need to make it more idealized. So let's think um, incompressible. Okay, liquid being incompressible. Well, if you have used hydraulics, that's using liquid, right, to basically amplify force. By having energy conservation, if you have a small force with a larger displacement, that does the same work as a larger force with a smaller displacement. But that is assuming that the liquid, whatever you're using, the working liquid in there, is incompressible or at least hard compress. So why does that matter? That's still an energy conservation argument. If the liquid can be compressed, then the compressional energy must be accounted for, right? Think about springs. We have springs with energy, elastic potential energy B12 because of compression and stretching. So if we take away the compressibility of a liquid, then there's no such elastic potential energy. So no elastic potential energy. It's not very difficult to account for, but it's also not easy, like 200 level easy. So if we take away friction, we take away any time dependence of the flow, we take away eddy currents, um, or energy uh, describing curls. We take that away, and also no elastic potential energy. So we're left with a bucket of ideal fluid. So this fluid is easy. Energy should be conserved, and the flow is kind of very smooth, and there's also no drag. Apparently, there's no drag. It's difficult to think about it as fluid. Stick your finger in water and drag your hand across. You just feel like something silky. It's very smooth and very frictionless, like silk, just going through without any drag on your hand. Okay, so that is the ideal fluid. And ideal fluids, especially the incompressibility, gives us a mathematical expression. So this thing here that I wrote last can turn into an equation. So the equation will say that the same volume into a certain tube or structure will come out as the same volume from the other end. So if you have, for example, a reducer, it reduces a certain diameter of a pipe. Let's just say from 2 inches to 1 inch. I'm just making it up. You can probably buy a lot of different size reducers in a hardware store, and I just don't have any need for those. The pipes have already been built when the house was built. So if I need to build something on my own, I might actually want to consider such as a thick pipe, right, to pass the main water current. And then if I need something such as I want to build an irrigation system in my backyard, and then the main pipe that goes into that irrigation system should be thick, and then it has a manifold of several smaller diameter tubes that maybe pipes that come out, right? So it depends on how I build it. So there's always this idea of reducing your cross section for this particular parts of the water consumption. So say if you have a few different zones in your backyard, and each one will be taking, let's just say, approximately one partial of that total flow, and there's no loss in volume. Let's just say there's no leak in your system. So whatever amount goes in, it comes out, right? So this idea of incompressibility can turn into a continuity equation. Okay, so what exactly is a continuity equation? It just tells you the volume that goes in equals the volume that comes out. So let's visualize that. Let's just say that we have a pipe, and then we have a reducer. So we have a thinner pipe. Okay, so water current flows in from one side, it comes out the other, and any practical experience should tell you that if water flows in like this, if you squeeze this right end, you're going to have a jet of water shooting out, right? So you can do that. And the idea is water flows in relatively slowly and it comes out faster if you have a narrow channel. So the idea here is the volume in equals volume out. There's a lot of these continuity or conservation equations. For example, in chemistry, the total mass of a reaction is conserved. So whatever amount of mass go into the reaction has to come out, well, including the gas products, right? So in physics, there's also energy conservation in a broader sense that sometimes mass turns into energy. So if you count that relativistic version of energy, then you still have the same total amount of energy mass before a reaction and after a reaction. That reaction could be a nuclear reaction, something breaks apart into different pieces, and each one carrying a total of less mass, but they also have energy that accounts for the lost mass, right? So, so this is a simpler version, volume in equals volume out. So let me draw some volume here. Well, that's a lot, and that probably accounts for all this. Okay, so let's just say this is volume in, all right? and this is volume out. Well, it's hard to actually do a visual comparison, right? I don't really even know if this is a circular or not. I'm drawing it like it's a side view of a circular cross section. Anyway, let me give it some area. So here's area 1, area 2. So the area is relatively stable where I was counting the volume, and it's not near the this reducer section. So what is the volume here? Area times this I'll call that delta x1. So that's a small thickness, and here's a delta x2, a slightly bigger thickness, but you multiply them together. So volume in equals volume out because of the incompressibility, and I can get, let's write on the right side. So V in equals V out. That gives us the area 1 delta x1 equals area 2 delta x2. Okay, so that's fair enough. And the delta x is, you can imagine, water from this interface flows for a short period of time until it becomes the front interface. Right, the back interface flows into the front interface. It also indicates this amount of volume, the shaded volume, has flown through. Right, so the delta x is just the back surface here flows into the front surface. So delta x should be x1 should be v1 times some sort of delta t, a small amount of time it takes to flow. And during that same period of time, the back surface right here flows forward into the front surface, and that translates into the volume has passed through, has flown through, right? So this is back surface flown this much distance at that different speed. We don't need to assume that water flows at the same speed. You have that experience. If you squeeze this end, you're going to have a jet of water. Okay. That's also how the sprinklers, anything, the shower heads, how they work. If you want jets, you want a smaller area. Okay, so with this, we're going to say that this equation is A1, delta x1 is V1, delta t, equals A2, delta x2 is V2, delta t. And we can divide out the delta t. We don't have to care about how much time we were watching as volume is flowing into one side out of the other side. It's generic enough. So this is the continuity equation. A1 V1 equals A2 V2. So that tells you that a larger area flows the liquid less fast than a smaller area that flows liquid a little faster, so that you can catch up. You can move faster with a smaller cross section. You can get equal amount of volume moved through, right? So that's how this works. And I can explain this with an example of highway traffic jam. This is always the case. The highway traffic jam is not because somebody is driving slow or somehow there's more cars. If you imagine that, if there's more cars, it's packed bumper to bumper. If everybody is just conscious enough and practicing safety, they're just driving and they're paying full attention. Why would they have to slow down, right? Well, it's safety aside. They don't have to slow down if everything's just moving with more cars on the highway. The reason they're slowing down is because of this reducer here. They're actually taking an exit, right? They have to take an exit, get onto a local road so they can go home or maybe get to their workplace. So when that happens, one lane slows down because this flow is slow, and the entire traffic will be affected until to a point that the whole highway is just stop and go. And while over here though, it still goes as fast as the highway exit can let cars out. So right, so this is actually relatively normal speed, although here many cars are getting to the exit, so they're really slow because there's actually more cars, more cross sections, more lanes trying to merge into the exit lane, trying to get out, and that slows down. Okay. So with a continuity equation, we can actually solve problems such as if something flows through with a certain speed, certain area, how fast is it going to flow through if you allow the area to reduce. Right. So let's have an example of the continuity equation. So let's assume we'll have a pipe, cross-section diameter of 25 millimeters, and water flow of make it relatively small, 0.40 meters per second. Encounters a reducer. Oops. Another pipe. Diameter of 12.5 millimeters. So we want to find the speed of water within the other pipe. Okay, so that's exactly the situation I drew on the left side. So I can just apply this equation. Remember, this is one equation, so we can only solve something like one problem out of one unknown out of this one equation. So that will go with area 1 V1 equals area 2 V2. So area 1 is pi R1 squared V1 is pi R2 squared V2, and we can divide out the pi, and we can recognize that the V1 R1 R2 are actually 1 to 2 to 1 ratio, 25 and 12.5, right? So if we plug in the values here, get rid of the pi's, so 25 squared times 0.4. The reason I'm not converting units is because the units will cancel out the velocity here. I can rewrite this as velocity times a1 over a2. See that the areas, if they have the same units, they'll divide out their units. So the velocity, whichever velocity unit you're using for V1, will be the same unit for V2. So as long as A1, A2 have the same units, they don't have to share the same units as the V's, right? So they just divide out, just like that. So 25 is in millimeters, and the 0.4 is in meter per second. So that does not really concern us. 12.5 squared V2. So we have V2 equals, I don't really want to squeeze that in there. V2 is equal to 0.4 times 25 squared over 12.5 squared. So we have a 2 over 1 ratio, right? 25 and 12.5, and we're squaring that. So we have a 4. So 0.4 times 4 is 1.6 meters per second. All right. So I can easily add another element to this question. For example, if water flows down a horizontal pipe at 0.4 meters per second with that diameter, and it flows into a reducer where it comes out with a different diameter pipe, and that pipe is horizontal. It's propped up against a table, and where does the water jet hit on the floor? Well, where does it hit? It's a projectile motion problem. You have to find the initial velocity in order to find where it hits. And the initial velocity is not where the water is flowing through the thicker pipe. It's where it flows through the thinner one, because that's where it is let out, into the air to become a projectile. So I can add elements together. It's like taking a little components and just glue them together into a composite question. So this is just one tiny teeny thing that probably fits the bill of a multiple choice question. But if I want, I can use this as a way to set up a projectile motion problem so that you can find the speed of the projectile, or also known as water, right? And then you can use that speed to calculate your projectile.